Conservation of linear momentum. Example: a 12 kilogram block of ice is struck by a hammer so that it breaks into two pieces. The 4 kilogram pieces travel at 16 meters per second in the x direction. So the x direction is a positive direction. What is the velocity of the other pieces? Intuition tells us that if a 4 kilogram pieces travel at positive x direction, then the 8 kilogram pieces might travel in opposite direction. So we should get a minus value, as velocity is a vector quantity. Simulation here. Initially, a 12 kilogram block of ice is at rest. The moment the hammer strikes, it breaks into two pieces in opposite direction. Make before and after sketches. The initial momentum of the two is 0, as the 12 kilogram of block is at rest. Initial momentum equals to a final momentum. And momentum is mass times velocity. We see that initial momentum is 12 kilogram times 0, as the 12 kilogram block is at rest, equals to 8 times v plus 4 kilogram times 16 meters per second, and that gives us velocity minus 8 meters per second. It indicates the 8 kilogram block of ice traveling opposite direction to the 4 kilogram of ice. Another example is a collision of cars. Conservation of linear momentum is applied to all types of collisions, in fact also explosions. Here, 730 kilogram smart car traveling at 25 meters per second positive x direction collides with a stationary 1800 kilogram of Dodge Charger. The two vehicles stick together. Find their velocity immediately after the collision. Best thing to start off is to make sketches. (730 kilogram of car traveling with a 25 meters per second to the stationary Dodge Charger. That's before the collision. After the collision, they travel with same velocity, and the mass is added up. So initial momentum equals to final momentum. Initial momentum equals to 730 times 25 plus 1800 times 0, as the Dodge Charger at stationary, equals to total mass. They stick together, so the total mass is 730 plus 1800 times final velocity. That gives us 18,250 equals to 2,530 times final velocity, and the final velocity equals to 7.2 meters per second. It indicates that two vehicles stick together and travel with the same velocity to the positive x direction, 7.2 meters per second. A loaded Glock 22 having a mass of 975 gram fires at 9.15 gram bullets with a muzzle velocity of 300 meters per second. Find the gun's recoil velocity. We use conservation of linear momentum. Initial momentum of the Glock and bullet equals to final momentum of the Glock plus final momentum of the bullet. Initially, the Glock and bullet are stationary, so 975 total mass times 0 equals to, we have to be very, very careful. After the bullet is fired, we need only the mass of the Glock, which is 975 minus bullet's mass 9.15 times the velocity of the Glock plus the mass of the bullet times minus 300. Here's minus 300, as we choose positive x direction as our reference, then the bullet is traveling in opposite direction, so minus 300. That gives us 0 equals to 965.85 v minus 2745. Final velocity of the clock is 2.84 meter per second in positive x direction. So the bullet is traveling negative x direction, then the gun's recoil velocity is positive x direction, which means like a reflected backward. Find change in kinetic energy of the gun bullet system. Find change in kinetic energy of the gun bullet system. Definitely we're gonna use kinetic energy formula. Initial kinetic energy equals to 0 as a Glock and bullet is stationary. We find the final kinetic energy of the Glock first, which is 1/2 times mass of the Glock. We have to be careful. Mass of the Glock is total mass minus the mass of the bullet times the recoil velocity of the Glock squared plus final kinetic energy of the gun, which is 1/2 times 0.00915 times 300 squared. That gives us 416 joule. Change in kinetic energy is final kinetic energy minus the initial kinetic energy. Final kinetic energy is 416 joule minus 0, which gives us 416 joule. Here, another thing is we need to convert the gram into kilogram, otherwise we cannot get a joule. Here we use unit of mass as gram because the gram can be cancelled out. But here we cannot use unit as a gram for mass, because in order to get a joule we need to convert unit of mass from gram to kilogram. Comparing elastic collisions and inelastic collisions. In an elastic collisions, kinetic energy is conserved. It does not change. The final kinetic energy equals to initial kinetic energy. Two billiard balls colliding in such a way that the speeds of the balls in a system remain unchanged. This is the perfect elastic collisions. A red ball has the same speed as a white ball. Both balls have the same speed both before and after. In elastic collisions, kinetic energy is not conserved. So final kinetic energy is not equal to initial kinetic energy. Example, a baseball and a hard ball colliding in such a way that the speed of the ball changes. In a completely inelastic collision, the colliding bodies stick together and ended up with the same velocities but different from the original. Two objects colliding and sticking together, we have seen before. Two trains collide and stick together. This is completely inelastic collision. A train cars hitch and move as one body. We have seen this before. Two cars collides and stick together. This is a good example of completely inelastic collisions. An explosion is similar to completely inelastic collision, is that the bodies were originally stuck together and began with the same velocity. Object at rest suddenly separating into two pieces, explosion, right? Block of ice broken into two by a hammer stroke, and bullet leading a gun. Two trains cars having equal masses 750 kilogram and velocities u1 equals to 10 meter per second and u2 equals to 5 meter per second collide and hitch together. What is their final speed? So we have a simple animation here. u2 and u1. u1 is traveling faster and they hitch and travel together. Initial momentum equals to final momentum. That is, initial momentum of the 1 plus initial momentum of the 2 equals to final momentum of the 1 plus final momentum of the 2. Substitute values, they are the same as, so mu1 plus mu2 equals to mv plus mv. You can see final momentums are same. So mv plus mv becomes 2 times mv, and the mass can be cancelled out. Final velocity equals to 10 plus 5 equals to 2 times v, and v equals to 7.5 meter per second. So the two trains hitch together and they have the same velocity, which is 7.5 meter per second. Now find change in the kinetic energy. We're gonna use kinetic energy formula 1 over 2 mass times velocity squared. Let us start with the final kinetic energy. Final kinetic energy equals to 1 over 2. Since they are hitched together and move with the same velocity, m plus m times velocity squared. That equals to 1 over 2 times 750 plus 750. The final velocity is 7.5 squared equals to 42,187.5 joule. Initial kinetic energy equal to train 1 over 2 times mass 750 times velocity 10 squared plus train 2 1 over 2 times 750 times velocity 5 squared. That gives us 46,875 joule. The question asking the change in kinetic energy, so final kinetic energy of the system minus the initial kinetic energy of the system. That gives us minus 4,700 joule. Determine the type of collision. Since the final kinetic energy is not equals to initial kinetic energy, this is in inelastic collision. And since the two objects traveling as one, this is also completely inelastic collision. And some of the energy lost as the thermal energy and sound energy to the surrounding. Was the mechanical energy conserved? Mechanical energy equals to kinetic energy plus the potential energy. We know the potential energy remain constant as the train is traveling on the same level. The kinetic energy decreased, so mechanical energy was not conserved. Was the total energy conserved? Energy cannot be created, cannot be destroyed. It always converted from one form to another form. That's conservation of energy. So definitely total energy is always conserved. The loss in mechanical energy is minus 4,700 joule. What happened to this lost energy? The lost energy is mostly converted to heat or thermal energy, some sound and possibly light, but very little, mostly thermal energy. Suppose 0.020 kilogram bullet, which is 20 gram, traveling horizontally at 300 meter per second strikes a 4 kilogram block of wood. It's resting on a wood floor. How fast is the block bullet combo moving immediately after collision? So let's visualize block rest and the bullet is traveling and they move with the same velocity. If we consider the bullet block combo as our system, there are no external force in the x direction at collision, so momentum is conserved. Final momentum equals to initial momentum. Final momentum equals to mass of the bullet times the velocity of the bullet plus mass of the block times the velocity of the block equals to initial momentum of this system, which is mass of the bullet times initial velocity of the bullet plus mass of the block and times initial velocity of the block. We substitute values 0.02 times v plus 4 times v. This is final momentum of the system, and n equals to initial momentum of the system 0.02 times 300 plus 4 times 0. Initially the block is at rest. So bullet and block moves at the same speed after collision. That's why they have the same speed. Final speed equals to 1.5 meter per second. Now find the friction between the block and the floor. We normally find the friction force using the work energy theorem. When friction force acts in opposite direction to the distance traveled. Work energy theorem equals to change in kinetic energy equals to work done. That is equals to final kinetic energy minus initial kinetic energy equals to work done is force times the distance times the cosine theta, and angle is angle between the force and distance traveled. Here, look at the diagram. The distance traveled is forward and the friction is opposite direction. The angle is 180 degree because the friction and distance are anti-parallel. Finally, the system at rest. So final kinetic energy equals to 0. The moment the bullet strikes and they move together, the velocity equals to 1.5. We found it from the previous slide. So final velocity equals to 0. So final kinetic energy equals to 0 minus 1/2 times the total mass 4.02 times the velocity 1.5 squared equals to F times distance is 6 cosine 180 degree, and that gives us F equals to 0.75 Newton. Find the dynamic friction coefficient between the block and the floor. We can find dynamic friction formula from our data booklets, which is equals to dynamic friction equals to coefficient of dynamic friction times normal force. Best thing to do is draw a free body diagram. So we have a friction force acting on it, we have the weight, and we have the normal force. In Y component, since the system is traveling in a horizontal direction, the net force in Y component equals to 0, which means R minus W equals to 0. That means R equals to W, that is mg. So total mass is 4 plus 0.02 and G is 9.81. That gives us 39.4 Newton. And we plug into our dynamic friction formula, and coefficient of dynamic friction equals to friction force divided by normal force. Friction force is 0.75. Our reaction force 39.4 equals to 0.019. So the dynamic friction coefficient between the block and the floor is 0.019. If the bullet penetrates 0.06 meter of the block, find the average force acting on it during its collision. So now we need to find the average force acting on it during its collision when the bullet penetrates 0.06 meter of the block. So we're going to use the same approach as before, work energy theorem, but we apply this only on the bullet. So changing kinetic energy equals to work done, and the changing kinetic energy is final kinetic energy of the bullet minus the initial kinetic energy of the bullet equals to force times the distance times cosine theta. And based on the interpretation and also our diagram, the average force and the distance travel is anti-parallel. So cosine theta is cosine 180 degree, which is -1. The final kinetic energy equals to 1/2 times 0.02, the mass of the bullet, times the final velocity 1.5 squared minus 1/2 times 0.02 mass times initial velocity is 300 squared equals to minus F times the penetration distance is 0.06 meter, and average force is 15,000 Newton.